Alright guys, chapter 13 would be explaining a tremendous phenomenon, an intriguing phenomenon called the electromagnetic force. Basically, electromagnetic force is the basis of functioning of everything that requires electricity to move, courtesy of Mr. Tesla, Nikola Tesla. The pioneers were Lorentz and, let's go to pen over here. The pioneers were Lorentz and Laplace. And those two guys independently worked on this electromagnetic force. Basically, it states that a current in the presence of a magnetic field will create a force. We call that force electromagnetic force. So the electromagnetic force, to be operational, it has to be acquired from a current and a magnetic field. So once again, a current alone wouldn't be able to create a force. A magnetic field alone wouldn't be able to create a force. You have to have both of them present. Okay? Both a current and a magnetic field would be able to create an electromagnetic force. A force which we call Lorentz force, Laplace's force, or the electromagnetic force. Okay? To understand a bit, this is one example. We'd be dealing with several examples, and all are ingenious methods of producing forces, mechanical actions. That is a rod that carries a current over here. And as that rod carries a current, if we place it in an area where we have a uniform magnetic field over here, as you see, this rod would be submitted to a force and it starts moving. Okay? It tilts from this equilibrium position. We'd notice that as the current, the intensity increases, that force increases as well. The angle between that phi increases. That means that the force is increasing. That angle between the vertical and the string that attaches this rod. And simple, if the current increases, it means those electrons over here, as they start moving, they would be moving faster. As they move faster, the magnetic field coming from those electrons would increase. And that magnetic field, this is the physics behind it, the conceptual behind it, that magnetic field resulting from those electrons would interact with that magnetic field, external magnetic field coming from that magnet, and they will either repel or attract each other, creating that force which we call the electromagnetic force. Alright? Now, as the magnitude of that field increases, as the strength of the magnetic field increases, we notice that this also deviates even more and more. Okay? So that means F depends on I and B at the same time. Okay, guys? Now, F would most definitely depend on I and B. But what about L and what about this angle over here? Going back to that, okay, if we take a look at this, as the length of the conductor, let's assume that that was the length of the conductor. This much length of the conductor would create a force that wouldn't be as much as this much length of the conductor, which is F2. And the reason is that carries whatever, so many current, so many electrons, that would be carrying way so many electrons. So all of those electrons would be now interacting with this magnetic field. So the force increases. Okay? Now, this is the explanation to L. As for this angle over here, if the length of the conductor over here is parallel to the magnetic field, then the angle would be 0, then the force would be 0. No force. That rod wouldn't be submitted to any force. However, if the rod is placed in such a way it's perpendicular to the magnetic field, alpha would be 90 degrees, then we'd find that the electromagnetic force would be maximal. And there's a function in math that introduces this. It's sine the angle. Whenever the angle is 0, sine 0 is 0. That's a minimal force, a 0 force. Whenever the angle is 90, that is a maximal force. So introduce that sign. So that gives you F to be ILB. Find the angle between LB. So it depends on I in ampere, L in meters, B the strength of the magnetic field or the magnetic flux density in Tesla, and F in Newton. To figure out the sense of the force, because as we characterize a force, we need its sense and its magnitude. The sense is given to us, guys. It's not Fleming's rule. We go with the right hand rule, okay? Because in UK, Fleming is done via their left hand. Anyway, you carry your right hand, stretch out your right hand. Your middle finger, this would be F. This would be B, and that would be I. So your thumb would be carrying the current, your forefinger would be carrying the magnetic field, and your middle finger would be carrying the force. So for example, if you have such a current and such a magnetic field, how would the sense of F be? If you hold your right arm with me, stretch your arm, place your fingers as you see in that figure. Now lift your hand such that your forefinger carries the magnetic field, your thumb carries the current I, so that gives you an F going to the inside into the page. That is the sense of F. Once again, FBI, your middle finger is F, your forefinger is B, your thumb is I, FBI. Now, align your forefinger with my B, your thumb with I, so F goes to the inside. That's one example. Another example is, let's assume this is B and this is I. Again, lift your right hand, align your forefinger with B, so it's going upward. Your forefinger should be going upward. I should be going to your right, so F, your middle finger, goes out of the page and into your face. Okay? Another example over here, let's assume this is I, and let's assume this is B. How would F be? So FBI, once again, B, your forefinger goes up, I goes into the page, your thumb goes into the page, and F would be to your right. Okay? This is how we find the sense of that force. Now, there are many, many applications on that, as I've said towards the beginning of this video. One of which is Laplace's rails. So this is Laplace's rail. That's set up over here. Okay? Now, you feed a current. You get a generator with its positive and negative pole. You feed the current over here. Goes in there. Follows through that rail and goes out to the generator and back again. It keeps on circulating. Now, once that rail over here goes in an area where we have a magnetic field, for example, let's assume the magnetic field goes from this north magnet to this south magnet, let's assume so, and the current goes as such, then it would be submitted to an electromagnetic force. And that force, if we wish to find its true sense, let's take a look. I goes as such, hold your forefinger, FBI, I is your thumb, it goes as such, and B goes downwards, so F would be that way. So this would be moving in this direction. Okay, take a look at this schematic. B is from north to south. However, over here, they've flipped the current, so that flipped the sense of the electromagnetic force. Another application is Cotton's balance. Another one would be Barlow's wheel. Barlow's wheel is brilliant. The first wheel invented using electromagnetic forces. Okay, that magnet over here with its south and north ensures the presence of this magnetic field. So we have a magnetic field all over this region. That, once again, you have a generator over here feeding a positive and into that circulation current, and each one of those spikes would be carrying a current going as such, dipped in mercury. Mercury is present over here, and its sole purpose is to complete the circuit. as we have a current flowing over here that ensures the presence of I, we have, this is I, we have a magnetic field over here, B, so you would have a force directed in this sense, let's assume, okay, or we have to find it properly, and then this spike lifts up, and then that leaves room for the next spike to dip in mercury, and then it would be submitted again to a force, and then it would move that way, and this would move downwards, and then you'd have a continuous motion for that wheel. And this is the modern Barlow's wheel nowadays. Okay, maglev trains work via the same rule. Those are very, very powerful magnets. They are used to levitate this train, and once this train is levitated, the train carries a current from on top. It's not seen over here. Okay, so you have the presence of a magnetic field and a current all over this, across like that, across the train, and a magnetic field and a current would ensure the presence of a force, and that force will drive the train forward and backward. Okay, we levitate it just to forget about and reduce all frictional forces. That would leave us only with air resistance and drag from over here. Now DC motors work the same, they follow the same principle. That ensures the presence of magnetic field over here. This is the magnetic field present. Now DC motor, you just feed it with electricity, and as that current flows over here, you'd have a current and a magnetic field, and that would create what we call the electromagnetic force, and that would go upwards while this would go downwards because of the sense of the current, and it keeps on flipping again and again. Loudspeakers do follow the same rule. We feed them with electricity, and as you feed them with electricity, that would carry a current, and the current in the presence of a magnetic field, that's an annular magnet. Okay, in the presence of a magnetic field, we have a magnetic field, we have an electric current, so both of those would be able to create what we call the electromagnetic force, and that force would be able to move this membrane over here. We have an elastic membrane, and this membrane starts oscillating according to the frequency of the current fed over here, so it starts producing sound. Alright, so those are many examples on electromagnetic force. Basically this is it. We care about the following: the sense of F, which is given by the right hand rule, remember, and the magnitude of F, which is given by I, L, B, sine the angle between L and B. Okay, take care.